are going to look at these scores today. Very similar to yesterday. Okay, so there's something called the SAT and there's something called the ACT, right? But the thing about the ACT and the SAT, they're different tests. They measure different things, and they also have different scoring. You would cry? You don't know what you're going to get? Nice. Okay. So, what a Z-score does, so check this out. So, if you have a score of 30, so if my mean is 23, and my standard deviation is 5, one standard deviation away would be a score of 28. Two standard deviations away would be a score of 33. So you would be somewhere in there, right? Correct? All right, so let's check out the SAT. So if the SAT has a mean of 1100, and one standard deviation is going to be what? What? 1250. And then 1250. Right? Add 150. And then 1400. Then you're somewhere in here. Aren't you somewhere in there too? Well, we got to find a way that you can find out which one you did better on. Can you tell which one you did better on right now?
No, I would say you did better on the ACT.
Would you? How would you defend that?
Okay, well, I was going to say because it's out of like 30 something, that's not a good defender. But then again, I guess it's never mind. Now another.
You can't really tell, right? Because 23 over here, 30. 30 is 3 away from being all the way up to that second deviation, right? And then over there, if you got a 1350, you're 50 points away. I wonder which one's better. Well, that's what a Z-score is for. You've got to make them comparable. Right now they're apples and oranges. What if I told you that somehow I could take the standard deviation and the mean and convert both of those scores into something that I can compare? There would be dividing involved. You're supposed to be thinking. What if I told you you had to divide by that standard deviation? I should have been using that on this one. That right there should have been an S, but that's okay. That is the new notation for standard deviation. Okay, it's kind of complicated. Statisticians think it's a really big deal. So when you see a M like this, it's an M, and it stands for population, the mean for population, and this is the standard deviation when you're talking about, exactly, sigma, when you're talking about a population. When we're talking about a sample size, we use S for standard deviation and X bar. It's the same thing, okay? The only difference is that formula that we were using. Remember this formula? That is for population. That is for a sample. There's your difference, okay? And when you put those numbers in a calculator and you do that, it's a difference of, it depends on the sample, but like when I had the key wrong for Mr. Taylor, and then I redid it with the -1, it changed my answers by like 0.2. Like it doesn't change them that much. What? Ask a statistician, because I think they're pretty close. So I don't know the answer. I don't know the answer to that question. If you don't subtract 1, you're not going to get the absolute correct answer. You got to subtract 1. Okay, and then if it was over n, it would be this one. Oh, thank you. There we go. Okay. So if I tell you you could divide by the standard deviation on both of these right here and have a comparable measure, what else do you think you need? Your score. What else do you think you'd need? Nope. No. What are we comparing to? When we find our spread, what is the spread in relation to? What? The mean, right? The spread. I didn't hear it. Sorry, Kane. But Christiana was right. She says that the spread has to do with the spread away from the mean, right? So if we're talking about the spread away from the mean, then we must be talking about, and you care about your score, what do you think my formula would be? Yep. And then divide by your standard deviation. That's what we're going to do today. Okay? So it matters. The difference between your score and the mean divided by the standard deviation is going to give us the same thing. All right. So here we go. The mean, median, and mode are equal, bell-shaped, and is symmetric about the mean. The total area that lies under the curve is 1 or 100%. Kind of just review from yesterday. Which has a greater mean? Wow, we don't have common consensus. C has the bigger mean. It's taller, right? Is that 17? 17 is the mean for this one. The mean on this one is 15.5. The mean on this one is 13, right? Which one has a greater standard deviation? Good. B has larger spread. Is a bell curve a what? No. Okay. So here's your normal curve, and this is just some data that is just up there, right? Here's a normal curve. When we convert it to a standard curve, it looks like this. So the standard curve, so you can compare apples to apples now. So a standard curve always has 0 for the mean, and then you talk about how far away. So a z-score of 1 is like 1 standard deviation away. And a z-score of 2 is like 2 standard deviations away. Okay, so it's just now we can compare the ACT and the SAT. You understand now? Good. Yes?
But how do you figure out, so look at the X up there, like that curve, that's not the SAT, right? And the bottom is going to be a score. How do you figure this out like this?
I'm going to show you. Okay? I love how you're always one step ahead of me. Okay, so on a normal curve, you can have any mean, right? Depending on the data, ACT and the SAT could be completely different. You can have any standard deviation, and your variable is X. When you transfer it into a standard normal curve, standard meaning we can compare anything to anything, right? That's why it's standard. Then our mean is now 0. Our standard deviation is 1. And then our variable is a z. Okay, so I have whatever my x value is minus my mean divided by my standard deviation. So let's go, you guys want to go back and see which score was better on the SAT or the ACT? Let's check it out. Okay, so if I have a score of 30, and I'm going to subtract that from my mean, and I'm going to divide it by 5. What's 30 minus 23? What's What's 7 divided by 5? Somebody tell me. Put in a calculator. I don't know by heart. How much? 1.4. Awesome. All right, so let's look at this one. 1350. We're calculating how far away it is from that mean, and then we're dividing by our standard deviation. So what's 1350 minus 1100? Well, but I want to write it. This is where this. Thank you. And 250 divided by 150, 1.6. So this one, they're over 1.6 standard deviations, and this one, they're over 1.4 standard deviations. So which one did you do better on? The SAT. That make sense? Yeah. You're going to see in a second because we use a special table for this. Okay. 2 decimal? Okay. Alrighty. So, this is called a z-table. This is why you're not going to Providence Stat? Okay. Miss Wiz used to teach Providence Stat. Okay. So, the z-table lists the probability accurate to 4 decimal places. So, this is what I was talking about yesterday when I was talking about probability as opposed to percentages, King. It is both the same thing, right? I just didn't want you guys to mix it up. So when I was talking about standard deviation, I just want to talk about percents. When I was talking about z-scores, and I was talking about probability. Okay. So these z-scores, here's your z-scores right here. Okay. And when you have a certain z-score, so what was the z-score for the SAT? 1.6? I'm going to pull it up over here. 1.6. 1.6 is right here. 1.600. I come down here. 90. I'm going to write it here. I get 9,452. That is the probability that someone would score that score or below. Does that make sense? 94%. So right here, the z-score for this one, I know that the probability is, or I should say, 94%, which was much more accurate. We had percentages in our normal distribution, right? We could say that 68% would score between here, 95%, so this is much more accurate. No, it means 94% of the population would score a 1350 or below. Like, right? Okay. So let's work with this. I want you guys to be able to play around with this. All right, so we're going to do a few. Why? No, you don't have to remember. You just have to know how to use it. That's it. Okay. All right, so I'm going to find the area to the left of z equal to 1.36. So 1.36 is somewhere right here, right? 1.36. So the area underneath this curve, let's read this. We're going to find out how much area, or the probability, right, that lies all the way in here. So if I want to find a z-score less than 1.36, let me go grab my table. Here's 1.3. I'm going to go across my table to 0.06. See that? It's kind of hard to see. So I'm lining it up. So 1.36 is right there. 0.915 131. Yep. Okay. Yeah, we can do another one. And then I'm going to get you guys a table of your own. In fact, let's do that right now. And then you guys can follow along with me. And your homework, we should be able to get done in class today, is only going to be the front side, okay? Just like the last one that you did. And then when we come back on Monday, we'll do the back side, and then we'll quiz, and then we'll test. Not all that on Monday. And then we'll be done with that. And we got to turn the cumulative in on Monday, yes. Bryce, it's not going to make a difference. I have another cumulative for you after you turn that one in. So wouldn't you rather have that next one earlier? Yes, you may. Andrew, come over here. Take one of these scores, or the tables, Z tables. All right, find the area to the left of Z equal to 0.98. Try it, guys, 0.98. 0.98. You want to find that area. Because you have negative z-scores too. Flip it over. Let's see, 0.98. 0.98 is 0.8365. 0.8365. How are we doing? Thumbs up, thumbs down. How you guys feeling? Okay, well, I got to show you a little bit more, and then yes. I love it. Okay, what about find the area to the left of z equal to negative 2.5? You guys tell me negative 2.5. Now, wouldn't you expect this area to be pretty small? Negative 2.5. Find the area left of negative 2.5. How much is it? 0.0062. Does that make sense? No, to the left. Here, the area to the left. This little tail right here. Wouldn't that be a very small amount? See what I mean? Yes. Yes, as soon. Oh, yeah. We're measuring the area under the curve, which is the probability. What? Well, no, it's a little more complicated, Anna. 0.15. It is, this area of this over here is 0.15, right? But we're talking even further over, like the exact. Like the whole area in that space is 0.15, but if you're over at negative 2.5 on the z scale, it's even less than 0.15. You see what I'm saying? Like it's a more accurate. You're absolutely correct. That's why we have z-scores, because they're more accurate than that normal curve. Okay? But they're totally related. Just more accurate. Okay, what about find the area to the right? So if you look at your z-table, you look at the top of your z-table, doesn't it only show the areas to the left? Yes. So you're going to have to subtract. Okay? So if I want to find the area to the right of negative 0.65, so negative 0.65 is somewhere like right here. Right? I want to find this area. But my z table is going to give me this area. Does that make sense? When I put in negative 0.65, I'm going to get this area. I want this area, so I'm just going to take 1 and subtract whatever this area is. Make sense? So if I want to find anything you want to find to the right, you're going to have to take 1 and subtract the left area. Okay, so find the left area for me of 0.65 on your z table. These are the negative numbers. You guys there? Let's see. Let's check. 6.5. Negative 6.5 is 2578. 2578. Can you put in a calculator for me? What is it? How much? 0.7422. Does that make sense? Right? If this is about 25%, isn't this going to be about 75%? Does that make sense? Yes? Okay. All right. So, it doesn't matter. Well, looks can be deceiving, right? That's why we have tables. What's the answer to that? I mean, they give it to you that accurately for a reason, so you should probably use it. Even though I don't totally agree with stuff like that, but when it comes to this, I'm guessing that that would be the right statement. Yes? What? Well, that's what they're just asking. You either need to leave it like that, 4 decimal places, but if you want to turn it into percents, you'd have to be 74.22%. You could write like that too. Yes? No, that was to find the z-score. Right now I'm just finding the area underneath the curve. No, your z-table only gives you the left side. If I want the right side, you've got to take the whole thing, and subtract this. I have to take the whole thing and subtract what I don't want. Your table only gives you the left. If you want the right, you have to take the whole thing and subtract the left. All right, try this one on your own. Instead of x, oh, I see. You guys see that? The mistake? This should be a z. This should be a z. Yes, Lana. I like it. Lama suggests I explain a little bit better. Okay, so if I'm going to find the area to the right of this score, so I want the area to the right of a z-score. So what happened, essence, was I took my mean, I subtracted it from, I took my score, my ACT score, I subtracted it from the mean, I divided by the standard deviation, and I got a standard score that I can compare to any other score. My standard score is 1.28, so somewhere around here. I want to find exactly the percentage underneath this curve. Specifically, I want to find the area or percentage of just this part of the curve. The whole curve is 100%. The whole curve is 100%. I need to subtract the left side of this table. The left side of the curve. 100% subtracting the purple part is going to give me this part, because my table will only give me the left side of the curve. Yes. You find the purple part, and you subtract it from 100%, and you get the area underneath the curve. Yeah, 1.28. So find 1.28 on your curve. What is it? What is it? Wait, 0. Okay, I've got like 3 people talking. I can't hear. Thank you. Awesome. Thank you. I appreciate you guys. 0.8997, is that right? Yeah. Okay. So if I take a whole and subtract that right there, what do I get? Wait. Hold on. Hope, tell me. 0.1003. Okay, does that make sense? So if I wrote this in percent, it would be 89.97%, right? So, no, you don't. I'm just trying to show it a little bit differently, because some people are confused by this, so I'm writing it in percent. So 100% of my curve minus 89.97% of my curve is going to be equal to 10.03%. Does that make sense? That this tail is only 10%, and the rest is about 90%. Okay? All right. One more complicated part. Find the area between 2 scores. Okay? So, if I want to find the area between 2 scores, here are my 2 scores. The area between 0 and 1.54. I want this area right here. But my curve is going to give me, I'm going to copy and paste this. When I do this on my curve, if I go over it to 1.54, isn't that going to give me all of this? So how could I just get this? Subtracting, right? What would you subtract? Exactly. You would subtract the z-score of 0. So, if I kind of want to just take this right here, so we don't have a bunch of stuff on our screen, and we can just play with this. Okay. So, if this is 0 right here, if I find a z-score of the purple, and I subtract the red, wouldn't I get the green? Yes. I know it's a little complicated. Okay? So, let's find the z-score of, let's find the percentage under the curve of the purple part first. So, what is the z-score, or the percentage, at 1.54? 0.9382. Okay, that makes sense. That's a lot of area, right, that we're covering there? So what's the z-score of a 0? What's the percentage with the 0 z-score? 0.5000. Does that make sense? Why would it be 0.5000? Because it's half. It's 50%. At 0, aren't you 50% of the curve? Right? We didn't even have to find that one. So I would take the whole purple part, the whole purple part, subtract 50%, and that would give me the green part. So 9382 minus 0.5000 gives me what? How much? 4382. Does that make sense? If you have almost a whole and you subtract half, aren't you going to, I mean, just look at your numbers. 9 minus 5 is 4. So you just got to make sure it makes sense. Are you guys ready for the homework? Start playing with this stuff? Okay. All right, let me pause this.